Hi guys, what we're going to look at today is kind of review for the two main topics that are going to be on the quiz. So the first one is simplifying radicals and the next one is adding and subtracting radicals. So when we were simplifying radicals, we looked at two different methods, and whatever method you like better, you can use. Method one was when we kind of made that factor tree like we did back in grade school to do that prime factorization. And then whatever that index is, that small number in that little radical spot, that's how we do our grouping. For each group, we take one factor outside of the radical. We multiply the things that are outside the radical together, and then we multiply whatever's left over together that's inside the radical. Option two is we look for that largest perfect square or largest perfect cube. That's a factor of that number, and then write the factor pair underneath the radical. And then you can separate it into two separate radicals and then simplify that perfect square or that perfect cube that we're dealing with. So let's look at some practice problems that we want to simplify. So in practice problem number one, we want to find the square root of 24. Remember, if there's nothing in that little index spot, we assume the index is 2, and the number underneath that radical sign is called a radicand. So here we want to take the square root of 24. For this one, I did a little bit of method 1 and method 2 to kind of help everyone. So the square root of 24, I rewrote that as the square root of 4 times the square root of 6. The square root of 4, we know is just the number 2, so there's no longer a radical, but square root of 6 is stuck how it is, so it's going to become 2 square root 6. Now, in problem number 2, I changed it ever so slightly by making it the cube root of 24. So now we're looking for perfect cubes. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and so on. Whereas in practice problem number 1, we're looking for perfect squares. So here, instead of using 4 and 6, I can use 3 and 8. I know the cube root of 8 is just the number 2, so it goes outside the radical, and the cube root of 3 is going to stay how it is. So here we have 2, the cube root of 3. Same idea in practice problem number 3 and 4. They're very similar, just the index is different. So in practice problem number 3, we have the square root of 54, x to the third, y to the fourth. So now we're involving variables as well. So remember our index is 2. So here we want to rewrite 54. I rewrote it as 6 times 9. And then x to the third means that we have 3 x's. Y to the fourth means that we have 4 y's. Think back to method number 1. We're looking for groups of 2 because that's what my index tells me. The cube root of 9 is going to be 3. For every kind of highlight that I did, I'm taking one of those variables out. Because this is really, what's the square root of x squared? Well, that's just x. What's the square root of y squared? I did it into 2 separate pieces, so you take a y out and a y out. Whatever I didn't highlight is going to stay inside the radical. So 6 stays underneath the radical and x stays underneath the radical. So our final answer, I just cleaned it up a bit and changed that y times y to y squared to 3xy squared, the square root of 6x. So once again here, I think we're looking for either you can kind of do that division with that remainder, that method, or kind of expand it out and look for those group depending on your index. So 2 different methods as well. In practice problem number 4, very similar, but now my index is 3. So instead of 6 and 9, I'm looking for that perfect cube. So that's going to actually be 2 and 27. I rewrote it, and then I have 3 x's and 4 y's. Remember, I'm looking for groups of 3. So the cube root of 27 is 3. I have 3 x's highlighted in red. For every grouping, I take one of them underneath the outside the radical. And I have that blue highlighting. For every highlighting of the y's, I take one outside the radical. What didn't I highlight? 2 and that y, so I'm left with 3xy, the cube root of 2y. Just make sure in here we're carrying down the index of 3 every single time, because if not, then we think that we have an index of 2. And 2 more we'll look at. So on practice problem number 5, we have the square root of 20xy to the fifth. So I wanted to break down 20. I thought of 4 and 5, and then I expanded the x's and expanded the y's. So the square root of 4 is going to be 2. And then all my groupings, I'm going to take one of them out. So the highlighting in red and the highlighting in blue, leaving me with 2y squared, the square root of 5xy. And last one, to practice some simplifying, the square root of 16, x to the 4th, y to the 6th. What we notice here is that everything's a kind of a perfect 16. I have 4 x's and 6 y's. So everything's going to go outside the radical. You can say square root 1 is left inside the radical, but that's just going to be 1. So we would say our final answer is 4x squared y to the 3rd. So once again, we can think about kind of dividing 4 divided by that index of 2, and there's nothing left over. So everything is outside that radical. So once again, we went over 2 different methods for simplifying. You can kind of make that factor tree and find that perfect square, expand all the way and circle depending on your index, or think about dividing the exponent into your index and try to do the remainder that way. So the next thing we're going to look at is adding and subtracting. Here, the main things that we want to remember is that you always want to start by simplifying each radical. Then we can add and subtract if these 2 conditions are met. If they have the same index, which is that small number, and the same radicand, which is a number underneath the radical. If both those conditions are met, then it's very similar to if we were adding and subtracting polynomials. All we do is we add the coefficients, the numbers in front, and we keep the radicand the same. So think back to Algebra 1. If we had 3x plus 2x, we could add them because they're like terms, it would be 5x. Notice that all I did was add the numbers in the front, the coefficients, and I kept the x's the same. I didn't change it to x squared. Same logic here when we're adding and subtracting. So in practice problem number 1, notice how it's 3 the square root of 2 plus 4 the square root of 2. It's already in simplest terms because there's no perfect square hidden inside that 2. They're like radicals because they have the same index and the same radicand. So all I'm going to do is add 3 and 4 and carry down that square root 2. So very simple. My answer should be 7 square root 2. In practice problem 8 and 9, we are going to have to simplify radicals. Because if we look at number 8, it's 4 the square root of 20 minus 2 the square root of 45. There's a perfect square hidden inside 20, and there's a perfect square hidden inside 45. So think back to what we did the previous page. I need to start by working with 20 and 45. So 20 I can break down as to 4 times 5. 45 I can break down into 9 times 5. I'm going to take the square root of 4, which is 2, and I'm going to multiply it to the number that's already there. So notice how now it's going to be 4 times 2, the square root of 5. And just like that back radical, the square root of 9 is 3, so it becomes 2 times 3 square root of 5. Multiply the numbers outside. Now I'm looking at 8 square root of 5 minus 6 square root of 5. Ask yourself, are both those conditions met in order for me to add or subtract them? Yes, they have the same index and the same radicand, the number underneath, both 5. So now I'm just subtracting 8 minus 6, 2, square root 5 gets carried down. I'm not making this square root 10, I'm not making it square root 25, we're keeping that exactly the same. Last one we'll look at. So in practice problem number 9, we see the cube root of 16 plus 4 the cube root of 2 minus the square root of 8. Notice my index is different. Keep that in mind when we get to our final steps. I got to start by looking at 16 and 8 because there's definitely a perfect cube hidden inside that 16, and there's definitely a perfect square hidden inside that 8. So let's simplify there. The cube root of 16, I can rewrite and think that it's 2 times 8. Perfect cube. 2 cubed is 8. And I can rewrite 8 as 2 times 4 because it's a perfect square. Index of 2. So now what I have to do is simplify. I can rewrite the cube root of 16 as 2 the cube root of 2. This middle term is already simplified, so I'm just carrying it down. And then I can rewrite the last term as 2 square root 2. I can only combine the first 2 terms because they have the same index and they have the same radicand. This last one has a different index, so it's just going to be carrying down. I can't combine it with anything. I can combine 2 and 4 to get me 6. Cube root of 2 minus 2 the square root of 2. So that's why it's so important to carry down your index so that you can make sure that you're only adding when you have the same index. Same concept we kind of did when we were in Algebra 1. I couldn't combine a 6x squared and a 3x because one has an x squared and one has an x to the first. Same idea here. If they have different indexes or different numbers underneath, if I had a problem that was like the square root of 3 plus the square root of 6, that would be as far as I could go. That would be my final answer. They have to have both conditions met. So hopefully that helped to clear up any questions that we might have had that we are posting about in the Google form as well.